For balancing redox equations, we have two methods of doing this. Option 1 is using half reactions. Option 2 is the method we learned way back at the beginning of the year when we just strictly look at oxidation numbers and counting electrons. For this question, I'm going to use the counting electrons method like I did in part A, which you can see above. So again, like usual, we start with the equation. Make sure you don't drop that negative attached to the iodide ion to start, because that will mess you up in the end, because this is an acidic solution, which means that we are going to need to count our charges. So any lost charges along the way will influence our answer and mean we probably won't get the right one. And iodine is usually in the liquid form. If you don't have the states, that's okay, because they're not given to you in the question. I've added those in there just as extra information. We start by figuring out oxidation numbers. When we have a pure element, its oxidation number is 0. I'm going to write these in red, just so we can distinguish them. So iodide, in its pure form, is part of the diatomic elements for the Hofbrinkel. So it is going to be 0 here, as it is written in its pure form. As opposed to on the left, as one of the reactants, I have it as -1. It's in its ion form. That means that its actual oxidation number is going to match its ion form, like -1 as well. As a polyatomic ion, we need to consider the oxygen in order to determine the oxidation number of iodine. Oxygen is always, always, always -2. There are 3 oxygens, so the total charge, in quotes, is going to be -6. The whole charge on this entire polyatomic ion is -1. So in order to create that, we need some number that's going to add together with -6 to give us -1. That number is going to be +5. So that is my oxidation number there. Alright, so now that I've got my oxidation numbers, I can determine what is gaining and what is losing. In this case, it's a little awkward because it's iodine in both cases. So, iodine ion, or iodide, is going to lose 1 electron. It becomes more positive by 1, from -1 to 0. This is per atom. The iodine that's part of the polyatomic ion is actually going to gain not just 1, but 5 electrons per atom, because it goes from +5 to 0. We need to check our subscripts to make sure that we know how many electrons are actually being lost per molecule. In this case, it's going to be the same, so it's 1 electron per molecule and 5 electrons per molecule. These don't balance out. They are not equal. So we're gaining and losing unequal amounts. We are not allowed to have lone electrons floating around in space, so we need to make them equal. Manipulating them with different numbers so that we get the same number of electrons gained and lost. So we have 1 times 5 is 5 electrons lost and 5 electrons gained. Once this part's done, you are able to answer any questions about oxidation, reduction, oxidizing agent, reducing agent. In this case, the iodine ion is oxidized. So the reducing agent is, it is the reducing agent rather. because that's all that is present. In this case, we can say that iodine is reduced, but it's not actually just the iodine that's the oxidizing agent. It's the whole molecule that it's a part of. So we actually can say that iodide, not iodide, but iodate is the oxidizing agent. So this is a key thing. It's a little bit different. In terms of what we're considering. So, going back to the original question, we don't really care about this. That was additional information. We need to write a balanced equation. Well, the numbers that we multiplied by right here are our coefficients. So when I fill in my equation, I'm actually going to have 5 iodides, and I'll leave my lone iodine as part of the iodate. So I look at this and I see, okay, well, I have 6 iodines on my left side, 5 plus 1. I need 6 on my right, so I need to put the 3 out in front. And that's great. This looks lovely. My iodines are balanced, but I have this this set of oxygen on the reactant side that I do not have on my product. So now this is where the acidic solution, that I forgot to acknowledge when I originally wrote the question, comes into play. Now I need to check the charges on both sides. On my reactant side, my total charges are 5 times negative 1 plus 1 times negative 1. The number out in front is the coefficient. The number in the brackets is the charge on that ion present. Which means that my reactants are actually at minus 6. My products on the other side have 0 charge. That makes that side really easy to deal with. Acidic solution means that we are adding H+. How that affects us? Well, for now, we're adding positives, and we need the left-hand side to be equal to the right-hand side. So the left is where we're going to add extra positives to increase that number until it gets to 0. So I'm going to add 6 hydrogen ions. Now we've added hydrogen ions. We already had oxygen on that side. So our big issue is that we now have 2 types of atoms that aren't on the product side. To counteract this, we're going to add water. Now we can look at the number of oxygens and hydrogens. There's 6 hydrogens, 3 oxygens, which makes it nice and simple to put the 3 in front of that water, and we are done. Everything is balanced. Hooray!